Good evening, everyone, and welcome to Nsimplex Pachinko. This is Obi-Wan Pez, your host. Uh, going to be working on some more mathematical thinking tonight. So, we'll see how this goes. Last time we got a little distracted talking about all sorts of awesome stuff and dealing with some quadratic nonsense that I was talking about over here. Yes. How's it going, Megalomorph? What was that last time? Not a whole lot. We got through 1/10 of one problem because we were just chatting about what was going on here. It was kind of ridiculous. Let's just say it's definitely not my class, because otherwise I would have been fired by now. All right, so let's see. These authors were going for the quadratic formula from a slightly different perspective. So they were saying instead of doing the standard quadratic formula, they wanted to say there was sort of a Babylonian model where they went with. That's fun. Okay. My cursor's different, and it like appears and disappears depending on where my. That's kind of cool. Although my buttons aren't working. Okay, I take it back. The Putnam problems. Oh man. Yeah, I stopped in for a little bit during that, and I was like, all right. So let's see. So the Babylonian problem said we're going to get two numbers, x plus y, which are going to get us a sum. X times y is going to get us a product, and therefore we can express or try to solve x and y for the sum and product that are given, because we can make two equations, two unknowns, and then voila, it turns out to be, oh look, it's a quadratic. Is that a nice little diac for you? So yeah, they come up with a quadratic formula. They go through this whole, I mean, it's kind of the standard thing, the um, complete the square and then come up with the quadratic formula through completing the square. And I said, you know what, I prefer it from the vertex method. So you say that a quadratic can be of the form, here we go. Quadratic can be of the form da, 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 y equals a times x minus h parentheses squared plus k, and then that means that we can get expressions for c and k, which then h turns out to be negative b over 2a, our usual thing, and then k ends up being this stuff. So c minus b squared over 4a, which then we can play and turn it into the quadratic going the other direction. What did x squared plus 2bx say to b squared? Yeah. Should have known that one. That's the other thing, is we don't teach completing the square at our school. Like, I'll do it in my 155 class, or like bring it up. I'll teach it in my pre-calc class. But yeah, I will not teach it in like any of my other classes at all. The first time that I like in my regular sequence classes, the first time that I actually teach it is my Calc 2 class. And most of them are like, oh yeah, I remember that from high school. And it's like, okay, do you remember why you're doing it? I'm like, because my teacher told me. I'm like, yeah, okay, we're going, we're starting over. Yeah, we're doing so much, you know, trig and um, even just the proper U subs with things that are squared inside, and yeah. Calc 2 is also like the first class where I can't just make problems up. I can't just be like, hey, let's try this. Oh man. One of my students roasted me the other day. It's just like, so you didn't prep this, right? I'm like, I'm about to kick you over backwards out of your chair. Just was under the impression this one would work out fine. Turns out it's not. Mm. Yeah, I feel like I don't want to use the book problems because like there are so few of them, and then I mean we could use the exercises, right? I guess I know that those are pre-vetted, so it'd be all right. Yeah, I mean it's not like it's random. But there were a few of them where I was like, let's find the what was it? Let's find the arc length of a parabola. Yep. That should have worked out better than I thought it did. Oops. I think my... That's what it is. Bamboo. Oh, liar. There's no problem with the driver. Oh, you know what? I'm on the wrong one. That's why. Because this... There we go. So I got a Wacom Intuos. I don't remember what this is. Yeah, Intuos. It was like 250, something like that. I figured, considering what I'm doing here on Twitch, this is. I mean, I actually can't do it this year because I wasn't making money. Because, oh yeah, like I've been using a free one. So I was using the little bamboo one that's like this big. That's probably about 15 years old. It was free. My boss gave it to me, and she was like, "See what you can do with this." And I'm like, "All right, sure." So I didn't use it for 10 years. It was just sitting around, and eventually I started making videos here at home. And I was like, remember that tablet that I had from you know 10 years ago that my boss gave me boss gave me for free. Hey, I can use that. So finally, it's it's okay. But the problem is that the it wasn't working 100% correctly. And there was something else that I wanted to like I don't remember. There was something else that wasn't quite working out. Like the utility is no longer supported. And so I was trying to throw the utility on my work machine, and they're like, no, it's not working. Like this driver just does not work. I'm like, so I bought it, bought this one, took it to work, um, and for some reason, like the plug and play works fine now, but it didn't before. So for whatever reason, it's working now, and I had to spend $250 to apparently appease the gods to make it work. The gods of the writing tablets are very fickle. But yeah, because I'm not like I don't know, I'm not using it on Twitch, so like or I'm not making money on Twitch, so like I can't use it as a tax write-off. I guess technically I could use it at work more often. Call it a work, call it a write-off, but at the same time, I don't know. All right, anyway, I've been talking too much. So I was trying to get out here and start my driver. Woo! Axe out of cord. How you doing? Oop, oop, there it is. Trying to still work out all of my trying to work out all of my drivers here. I have been having a hell of a time trying to install um, the new service pack. So for whatever reason, it just does not want to do it at all. So 20 what is it 21H1 is not doing it. All right. Okay. All right. That is not a writing implement. All right, so proposition 1.1. If we got 0 less than A less than B, then A squared is less than AB is less than B squared. Fun times. And 0 is less than root A is less than root B. All right. So this should not be a difficult problem, and I'm trying not to look at the answer here. All right, so we should be able to do direct proof pretty easily. Okay, so if we have this, then we should be able to take A and multiply it onto all parts. So that's going to be A squared less than B squared. That's not what that says. Whoops. Oh, come on. There we go. Come on. less than AB. And also, if we multiply b onto all parts, then 0 is going to be less than AB. It's going to be less than b squared. Okay, so by doing transitive property in this particular case, zero is going to be less than a squared, less than ab, less than b squared. Okay, so that's part A. And also we have the square roots here. Hey, Benji boy. Welcome. We are looking at a book that is called... What is this? I wrote it down here. Yeah, Mathematical Thinking, Problem Solving and Proofs. So we're just playing around with some algebra. This is a book that I believe my spouse had in one of her either proofs class or analysis class. And I've just never gone through it, so I figured, try it out. It's mostly algebra, but like, slightly higher algebra than you get into in high school. But if you are at all interested in asking any questions, feel free, drop it in the chat, and I will get to it whenever we reach a convenient break point in whatever problem I'm doing. And we don't have to necessarily finish my stuff. This is just time filler, essentially, and, showing people different ways of thinking about math, depending on what we're looking at. All right, so I'm looking at this, and I'm saying, okay, we can't necessarily... I mean, we can, because we know we can do it, but I don't think you can just take the square root of all pieces and just be like, aha, see, it's less than. Because, again, you have to sort of prove that that property works. Absolutely. Which area are you working on? All right, we're getting a little warm here. Probably shouldn't have worn fleece pants. I decided that I had had enough of my khakis for the day, so... So, let me know if this is valid. Because I believe that we could essentially substitute and say, like, oh, well, we have basically like an M and an N here, and these things are root M and root N, but that's using the converse, so that's not really... Like, it's not logically equivalent, so we shouldn't be able to do that either. Oh, nice. Is that like through your school? Through your printing department, or I know some schools like have an actual like book press that they go through. Yeah. Yeah, I've done several uh, dozen hours worth of videos, and then like when the pandemic hit, I went through and did about a dozen more, and then I was like, eh, like I'm streaming, and then that's about as much effort as I can put into it at the moment. I just got so much other stuff on my plate. Very nice. Yeah, Benji, if I wasn't clear, go ahead. Sorry, I got distracted. It happens. And if you're still typing, I apologize. It's fine. So transitivity is an interesting and fun property. Um, transitivity says that if A is, well, we'll go with less than at the moment. If A is less than B and B is less than C, then A must be less than C. So this doesn't have to be less than. It could be a lot of different properties. So one of the things that we explore in mathematics is say, like, here's, yeah, it works for all sorts of equivalence relations, is what we call those classes. So something like equality, something like less than, something like greater than, and naturally all of the other ones that work with that, greater than or equal to, less than or equal to. Um, yep, and we have a whole bunch of different operations that we could come up with. Sorry, relations. So if the same relation holds from A to B and from B to C, then we want to test whether the same relation is going to hold from A all the way out to C. And if it does, then it's transitive, that particular relationship. So this is one of the things that I've been kind of harping on with my students and occasionally here, is that really we want to focus on, in all of mathematics, we want to focus on relationships. So that's everything in math is going to be based on relationships. And not just between numbers, but, you know, what kinds of structures can we create? Oh. Yeah, so Megalomorph, let me know. That's not my theory for this, or my hypothesis is not correct, right? We're not allowed to use converse by saying that let this be m, let this be n, and oh look, it's uh, root m, root n. Sure. I figured not. uh, so not converse. I don't know if it helps any, but you might be able to turn down the settings. I think I might not have that. You can downscale your quality to like 360 or 120 or something like that. Maybe. should be able to look at it, right? No, it's only 720. Oh well. Maybe I need to work on that. Alright, so it's not going to be commutativity, it's not going to be the thing. That's not what I said. No, I was looking at the quality. So the only option that I have in my quality is 720p. And besides, if I said it's 720, my clock is so far off. No, I've already said that I work in the Mid-Atlantic. So so over here, what we did was we said let's take every single term and multiply by a. And since we know that a is a positive number, then we're allowed to multiply across, and it doesn't affect the less than symbol. So if a were a negative number, then we'd have a problem where all of our less than, greater than relations would flip. So it'd be pretty awful. So we say here, since a is a positive number, we can multiply all terms by a. And same on this one, if we take the original and multiply all terms by b, we get the third row here. Fair. I think the lag would probably be a little bit more. Boo. Alright, so all this stuff ends up going here. And then if we multiply by b instead on every term, that'll end up going down to this row. Okay, so to Benji's point, my point with doing this is then we say, okay, if 0 is less than a squared and a squared is less than ab, then 0 is less than ab and ab is less than b squared. Sorry, if and. Then we're allowed to say, okay, well, this a squared is going to fit between 0 and ab, because we already have it from the first row here. So we might as well just combine these. So if a squared is between 0 and ab, then we can fit it in down here between 0 and ab on a new row. And then if b squared is above ab, then we're allowed to do that on the last row as well. So just combine everything into one disgusting, gigantic compound inequality. Was that it, Megalomorph compound? Zero is less than a and 0 is less than b. Take the square root of both sides. 0 is less than square root of a and 0 is less than square root of b. Is it compound? Is that the C word we were looking for that one? And a less than b. That's fair. Oh, yeah, okay. I mean, we're not going to be able to... Oh, yeah, yeah. Affirm the contradiction. Gotcha. The stuff up there is actually from a different problem, so... So the stuff up at the top there was looking at doing the quadratic formula from a slightly different perspective. So I had so the way that I teach quadratics is that I use the vertex method, and so I use this vertex formula because I actually teach all of like my entire pre-calc class is centered around taking all functions as linear transformations. Now, it doesn't work when you're talking about like, some crazy polynomial, but all of the parent functions of quadratics and cubics and quartics and whatever else can be done individually as um, linear transformations. And then we start playing around a little bit with like, okay, now that I can take this thing, I can move it somewhere and I can stretch it this way or compress it this way, then we can come up with like what structures does that create for us. So again, here you're probably used to the where you go, this one, right? 0 equals, or f of y equals ay squared plus by plus c. It's probably more what I shouldn't assume, right? It might also help to ask what level you're at. But, yeah, sorry. Anyway, so we come up with this quadratic, or y equals ax squared plus bx plus c. And then we look at it and say, okay, if that's our quadratic, and also, this is also our quadratic here, y equals a times the quantity x minus h squared plus k. How are those things related? And when we relate h and k to a, b, and c, then we start being able to, again, no, that's fair enough. uh, at this point, je parle Google Translate. So, so anyway, this was looking at quadratic equations. So trying to take something that looks like y equals ax squared plus bx plus c and relating it to the other one there. You're forgetting an accent. Or several. All right, so this one is saying if we know, it's fair, if we know for a fact that a and b are both numbers that are positive, so greater than 0, but a is less than b, then we want to prove that a squared is less than b squared. Nope. A squared is less than ab, a times b, which is also less than b squared. And also, we want to prove 0 is less than the square root of a is less than the square root of b. So in this case, is we've shown on this side that if we multiply each part by a, then we get this 0 is less than a squared is less than ab. If, on the other hand, we multiply by b, we end up with 0 is less than ab is less than b squared. And then by taking those two statements and putting them together, we end up with 0 is less than a squared is less than ab is less than b squared, which was one of the things to be proven. So we've shown this one. If 0 is less than a is less than b, then a squared is less than ab is less than b squared. Okay, and taking this and statement here, we can separate it into two cases. So if we have 0 is less than a is less than b, then a squared is less than ab is less than b squared. We've just proven. So this is good. Now we have to go to the other case over there and say, all right, if 0 is less than a is less than b, then 0 is less than root a is less than root b. And Megalomorph was just helping out here and saying, okay, we can't prove it this way. So it doesn't work. But, yep. But proving it by direct proof is not going to work. So, in this case, we can't do it. You're terrible. Makes much more sense when you know franglais. So this is a direct proof, where we start with a known fact, and then we use those facts. Oh no, this is fine. Don't worry about it. And if you want to get your actual question here, you can feel free. But anyway, a direct proof is when you start with a known fact. So we said if 0 is less than a is less than b. So we take that as our assumption, that this has to be true. Then we go through and say, okay, if that's true, then we need to show that a squared is less than ab is less than b squared, which we did. And also, we need to show that 0 is less than root a is less than root b, which we can't do. So, instead of a direct proof, which again leads from a given principle to something that we can find. So in this case, if we start here, we can't end here. It doesn't work. So instead, what we're going to do is do something called contrapositive. Now, I don't know what the French word is for that one, so... Contraposé. Okay, switch. And contrapositive. Contraposé. So, not that it necessarily helps you because you're, again, in algebra. And this is like a... this would probably be a little more advanced. But anyway. Contraposé. Would say instead of trying to prove it this way, we're going to try to prove it this way and also make both statements negative. So we're going to say if not 0 is less than root A is less than root B, then not 0, and nope, that's supposed to be a 0. 0 is less than A is less than B. All right. This looks annoying. So let's see. That. All right, so this is 0 is less than root A and root A is less than root B. So not that is going to be, oi. Yeah, okay. So we only need that one part. Okay. So root A is less than root B means that the square root of B is greater than or equal to the square root of A. If this, then not this is going to be, again, this is A is less than B is the appropriate part, so not that is going to be B is greater than or equal to A. Yeah, I guess. Oh, fine. I guess we're going to have to do things in the normal sense. Right, so I mean, I guess that's just literally the same thing we had before. So, yeah, cool. So take square root of b greater than or equal to square root of a, and then take all parts and square them. And since a and b are both going to be greater than or equal to, well, just greater than 0, but realistically it could be 0 also. And since a and b are greater than 0, and this is, right, root b is going to be squared and root a is going to be squared, then they preserve their positions on the number line relative to each other and relative to 0. Opposite of Mwenda. Plus grand que. So b is going to be greater than or equal to a. And then that's what we wanted from the stuff. Alright, cool. Oh, no. This is all easy stuff. Now, granted, like, you know, the class itself is actually a usually sophomore level of college, and generally speaking, math majors, and like people who need to do um, people who need to do hard science. So typically, you know, physics, probably computer science. Forget who else we got in there. Okay. Do. Okay. Okay, so this is the thing with contrapositive. So what we're saying is that we're going to assume the opposite. So we start by saying if this is not true. So square root of a is less than square root of b is false. That means that the square root of b has to be greater than or equal to the square root of a. Now wait, I did that backwards, didn't I? All right. I did that backwards. Okay, so we have to assume the opposite. So if square root of a is less than square root of b was our original statement, and now we want not that, then we're saying that if the opposite of this is true, which is that the square root of a is greater than or equal to the square root of b, okay, opposite statement, then the opposite of this is going to be true. So a is going to be greater than or equal to b. Oops. I do that all the time in my regular classes. Drive some of my students nuts. Others just think it's funny. Okay. So root a squared greater than or equal to root b squared. And since right, a and b are still positive numbers, then we end up with these things, which get squared. So this is just going to be a greater than or equal to b. Okay, now we've got it. So again, with the contrapositive, what we're going to do is we're going to take the statement, reverse the order, and also make them both negative. So when we do that, we're able to work out a different statement, which is easier to prove. All right, give me 1 second. I'll be right back. Okay, it's weird. Yay, technology. Woo. Yes. So finding the square root of a squared, like that, is then just going to be a. Because those are inverse operations of each other. So if you were to take like a plus 2, then the inverse operation of this is going to be take that thing and subtract 2. And then when you recombine these, you just end up with a at the end. Now, typically this is in a context. So we say, like, for instance, if we had had a plus 2 equals 7, right? The inverse operation here is just like if we had a negative 2 on, or a subtraction of 2 on the outside compared to an additive 2 on the inside here. Not really useful. It can simplify some stuff. Here with an equation, oftentimes what we do is we say, okay, if we want to still ensure that the balance is kept between the two sides, then we want to take the inverse operation of whatever's written here in order to get a by itself, and also remove this 2 that's here. We don't really want that, or same thing really. In order to balance it, we also have to take 2 off from the other side. So if you think of it like the pan balance, like, you know, scales, whatever you take off of one side, you also have to take off the other, because otherwise it becomes unbalanced and then you get a scale that tips. We don't want that. We want everything to stay balanced exactly the way it was. Yes. Yep. So this is the way that I often write the algebraic notation. So the way that we do this is we say, okay, let's add an equation underneath it to this equation. You ensure that the equality signs are in the exact same place. And then this one is just same thing on both sides. Yeah. So I typically will add in the equality sign underneath. Most people don't bother. Most people will do something that just looks like this. Again, I prefer to make sure that we're not accidentally, because some of my students have done this, subtracting 2 twice on the same side. So for instance, there was somebody who did like 2 plus a minus 4 equals 3 or something like this. And what they did here was they said, I'm going to subtract 2, subtract 2. And then here, this is 0, this is a, and this is minus 6 equals 3. But notice that if we do this, we're going to get a different... I shouldn't use a. Not the same number. B. Notice that if we try to solve this using the same stuff as we did here, versus if we try to solve this one, we're going to get 2 different answers. So like this one, we're going to add 6 to both sides. This is going to be b equals 9. But here, if we do this properly, this is going to be b plus 2 minus 4 equals 3. We're allowed to commute 2 different numbers, or 2 numbers, with addition. So the b and the 2 are being added. Switch. And now the numbers are next to each other here. So we get b plus a negative 2 is equal to 3. And then again, here we can add 2 to both sides. And we get b equals 5. Well, this and that form a contradiction. All right, so for that, that's a more complex equation. Not too bad, but slightly more. And for that, we are going to want to use order of operations to make sure that we're moving things in the right locations. And yeah, but that's an operation. Like that's an operation that's being done. Okay. So I mean, addition's an operation too, and it's the whole side. Um, but this in particular ties into um, solving systems of linear equations. Like explicitly ties into solving systems of linear equations. So that's where my connection is with this. So I'm using the same method to do that, which again is slightly different. Okay, let's take this and cut new and paste. Woo! Okay. So, for example, if we do a plus 2 is equal to 6 plus 4, how much of that do you want over 2? Do you want that just 4a over 2, or do you want the whole side over 2? Whole thing. Okay. Yep. All right, so if we do this with the whole thing over 2 like that. So, there's a couple ways to go. First of all, because 6 and 4 have a common factor, you can pull out the common factor. So the common factor between 6 and 4 is going to be 2. And then you're left with 3 plus 2a. This is all divided by 2. And then we're left with a plus 2 on the left. So, now that we look at this, you notice that this is 2 divided by 2. So that's nice. We're able to divide these out. It's just going to get 1 over 1 as an equivalent form, or just 1. Then we're left with 3 plus 2a is equal to a plus 2. Right, which is why I asked. The both of us have been doing this long enough, right? All right, so in this case, now we need to adjust so that everything is back on the same side. So we want all of our a's to be together. Now, me personally, I like to keep my variable terms positive. So I'm going to move the one that has fewer. So this is 1a. This is 2a. and both are positive. 1 is less. Yeah, no, I got you. So 1 is less, or 1 is more negative than 2. And so I'm going to move the 1. So 1a. So I'm going to subtract a from this side and subtract a from this side. I'm also going to get rid of the 3 from this side because the a's want to be on this side. I don't need the 3 here. In fact, I would really prefer it not be there. Okay, so now our a subtract a is going to be 0. 2 subtract 3 is going to be negative 1 equals 3 subtract 3 is 0. And 2a subtract a is 1a, so just a. So a equals negative 1 from your above case. And then we can prove it, or not prove. We can show that this works for this function, for this value, not function, equation, by saying, okay, if we do negative 1 plus 2 is equal to 6 plus 4 times negative 1 divided by 2. On the left, we get negative 1 plus 2 is just 1, is equal to 6 plus negative 4, 6 minus 4, is going to be 2 over 2, which is 1. We can stop there. You could go one further and just say it's 1 equals 1 to be like doubly sure that you're absolutely going to get to the end. But as far as like I'm a teacher, I don't really care that much. As long as you're showing me something that's pretty obvious, I'm happy. Yep. Yep, no problem, Megamorph. Have a good night. See you on yours. Or mine later. Who knows? Thanks for stopping in. Alright, Benji, if you got any more, let me know. So some of the fun stuff about algebra, just in general, is that this was actually the entire like subject of algebra was created by a guy named Muhammad Ibn al-Musa al-Khwarizmi. So al-Khwarizmi is his, last. Yep. So if you were to do something similar to this, we could do like 4a minus 3 is equal to 6 minus 2. Let's not do 2. Something that's slightly harder. 6 minus 5a all over 2. Right, so something similar, but not quite exactly the same. This is not going to divide nicely. It doesn't have the common factor that the other one did. So here in this case, we're going to have to do the other thing, which actually I didn't talk about up here, but the other option was to get rid of the fraction first. That's my preference for this one. So I'll give you a couple minutes on that one. Or you can ask more questions. Sorry, ask more questions about this or ask more questions in general. Your choice. So Al-Khwarizmi was a 13th century mathematician. Muhammad ibn Musa al-Khwarizmi. Yep. Oh no, way earlier. Okay. So, man, I thought he was like the 1200s. No, no, no. He was born in 780. So his main work was in the 800s CE. So, so Al-Khwarizmi was around in the 800s, and what he did was he came up with a systematic method of uh, doing what we now call algebra. But back then, his main work was a very large book with a very large title. Um, so the full title was The Compendious Book on Calculation by Completion and Balancing. Or, with apologies to anybody who actually speaks Arabic, Al-Kitab al-Muqtasar fi Hisab al-Jabr wal-Muqabala. So, in and amongst all of that, the title got shortened from that much larger title to just the one little thing, which basically meant completion or balancing, um, which is Algebra. So out of all of his work, they just chose that one word and said, okay, we'll call it Algebra. So the systematic approach then became named after him, the Al-Khwarizmi method, or an algorithm. Uh-huh. And Al-Jabr became algebra, which again is very similar in French, algèbre, and I don't know algorithm, but I'm pretty sure it's very similar. Uh, yeah, algoritme. Damn it, that didn't work. Anyway, okay, so take out the fraction, multiply by 2 on both sides. Yeah. So multiply the entire right side by 2, multiply the entire left side by 2, and yeah, we get the 8a minus 6 is equal to just the top part, 6 minus 5a. Again, for the same reason as before, we're going to end up with a 2 divided by a 2. So that's just going to be a form of 1. Yeah, he was definitely a genius for not just for his time. Like if you brought him into today's society, right? And he was able to study all of the advances we did since then. Um, he would, yeah, he would have. I think you'd be probably somewhat impressed. Yes, Bertram. Al-Khwarizmi is his name, and then people started passing the name Al-Khwarizmi down through the centuries, and it started getting bastardized into this new word algorithm, which represents, again, a systematized approach to doing something. So his name got turned into a word that represents the method. And again, the one word from the title, Algebra, ended up becoming algebra. Well, I mean, if you think that's bad, you should look at some of the old stuff that they had, like prior to him. Everything was in words. Like all they had were pictures and words. There was no notation. That's also fair. So yeah, before him, like I said, there was no notation. He decided, why don't we take letters and start representing numbers by them? And then we can say, like um, I mean, maybe not surpass, but I think he could give people a run for their money if he was able to, like, if he had time to um, start from like where we do our basic algebra stuff and move from there. I think that he would understand calculus without much trouble. Where he goes beyond that, I have no idea. Like, so the another couple of things about um, mathematics is that it's also kind of cultural in the sense that like where your culture is determines kind of what you can understand. It shouldn't be that surprising, I guess, but um, so one of the problems with Europe back in, you know, everything up through the 1500s was that their philosophy did not allow for um, things like the number zero. Everything kind of had to be tied to some sort of application. And so if you're saying like, well, how do what we know of as negative numbers make sense to them? And the answer is they don't. There are no numbers to represent that. It was just like a positive number and a direction. 12/13. Seems right. Okay. So yeah, add 6 to both sides, add 5a to both sides is the preference. So if you add 5a, you're going to end up with the 13a on that side and the 12 on that side. And yeah. Algorithm is his name. Yeah. So it essentially became the Al-Khwarizmi method, however that translated. And then eventually people just dropped the method part of it, and it was Al-Khwarizmi. Yep, you absolutely got it, Benji. Right, and keep in mind, this could have been done the other way too. So 8a minus 6 equals 6 minus 5a. You could have moved your negative 8a the other way, and then here subtract 6 from both sides. This will get us a negative 12 and a negative 13a, which when you divide by negative 13 gets you a is still, well, I mean, it's the same thing, so might as well just do that. A demon, you say? So, if you actually read the book, or its nearest translation, um, then basically he goes through a list of steps that get you from having a mathematical problem to then being able to solve it by moving stuff around. Yeah, no problem, Benji. Thanks for the follow, and we'll see you around. I do Wednesday night math streams, and I do Friday night just faffing around, mostly with games. And yeah, sure. Um, lately, I've been playing Trail of Ayash, which is a um, well, it is a uh, third-person slash hack sort of game um, where you run around and pick up loot, stuff like that. Third-person chase camera. So your person is an indigenous member of a South American, I think, I think Incan, but I'm not sure. I don't think they're very, or like pre-Incan, um, in the pre-Columbian society. So before Europeans ever came to America. Uh, and then some of the monsters that you come across are like the mythical monsters of this particular society. So I'm really excited to get into like more of the game. So far, it's just been like fighting against other people, and so it's uh, other indigenous peoples from different tribes. So like it's yeah, I've been looking for looking for food and grabbing stuff all over the place, and then trying to sell to people. So it's kind of at the moment, it's a little bit like I don't have a good example. Some sort of dungeon crawler, similar to not quite Diablo, but something similar to that. Which I'm up for that. But at the same time, I can't wait to get into like the bigger battles where we're fighting mythical monsters and cool stuff like that. So currently, it's just war. Yeah, I don't think I know enough about RuneScape. I was like, oh, Dungeon Siege, but A, that's such an old game, and B, Dungeon Siege is like Diablo, isometric cam. So you're stuck in place, and then you just like follow. You're always in the center of the screen, and the camera's like way back overhead, or bird's eye view, or whatever. Oh, right, like WoW. Idiot. Come on. Ugh, I've played games like this before. Come on. Anyway, yeah, so WoW, RuneScape, all that good stuff. Similar to those. Okay, so what you got, Bertram? No worries. I'm gonna write down the next problem that I'm working on somewhere else over here, but do your thing. All right, so this was definition 1.2. Absolute value of x is defined as x if this is greater than or equal to 0, negative x if x is less than 0. And I'm going to argue that actually I'm going to define this as the absolute value of x minus c. It's going to be equal to either x minus c when x is greater than or equal to 0, x is greater than or equal to c, and c minus x when x is less than c. Okay. Nested quantifiers. So universal and existential. Okay. So if you're looking at where'd you go? There we go. Oh my god, come on. So if you wanted something like P or Q and P and not Q. Something like this, or is it more like if we do not P or not Q? That's all right, and especially if the ones you can use for text are the like or is V and is just the caret on top of 6, shift 6. You can also use the emoji keyboard, which let me see if I get this right. It's like Windows space or something. Nope. No. What did she say it was? One of my students said it. No. That was not it. For all. I see. So we're not doing that one. Okay, so for all x, there exists a y such that 2x plus y is going to be greater than 0. Mm-hmm. Okay. No. No, so this is saying that anytime that you pick an x value, so you go off and you pick an x value, and for any x value you pick, I can pick a y value, which will make that expression positive. So you're like, okay, I'm going to pick negative 5 billion. And so um, having negative 5 billion multiplied by 2 is going to be negative 10 billion. And I'm going to say, I'm going to pick a y like 10 billion and 1. And now 2x plus y is going to be a positive number. So all that I need to do is be able to say, no matter what x value you pick, I can always pick a y value that will make 2x plus y into some positive number. Now, it doesn't have to be the same one, right? And that's key, because eventually, as your x values get more and more negative, as your x values get more and more negative, I have to keep picking bigger and bigger y values. But the point is that I can always pick one somewhere within the scape, within the within the appropriate values of y that will still make 2x plus y positive, no matter what. So realistically, if you're taking this and you look at it and you say, okay, what does y need to be? What relationship will exist between y and our x's? Yeah. So it doesn't always have to be greater than 0. So the point that really I'm trying to make here is that the y value is going to depend on the x value that's chosen. So we can make an inequality out of this one that, again, y will be dependent upon the value for x. Oof, goodness. Yep. If you let x be the independent variable, y be the dependent variable, then again, you're saying here, no matter what x you pick, I can pick a y value that's going to make this thing true. So therefore, my choice of y value will be dependent upon your choice of x value. And that's the other thing, is that I only have to show that one y value works. You have to go through every single x value in order to like find every single one. Now, realistically, we don't have to do this. It's just we show what relationship exists between the x's and the y's, and then show that, okay, well, if you pick any x value, I can pick a y value that looks like this. And as long as it looks like this, then I satisfy the other part. All right, sorry. So, so generally speaking, when you're just talking about independent and dependent variables, both of them are fairly likely to change, but the independent variable is the thing that just kind of goes by itself, or I have no control over it. It's going to be, again, your choice of x. Me, on the other hand, my decision is going to depend upon your choice. In terms of like regular scenarios, right? We could say that like distance and time, the distance that you travel is going to depend on the time you take to drive in your car, right? And generally it's going to be, I don't know, something like this with a constant speed. Um, we could also have uh, the times that are done in races. So if you time a bunch of people doing foot races, or like one person doing foot races of different kinds, then usually what you're going to see is you're going to have data that looks something like this. And that just flipped our independent and dependent variables, because if you have one person running a bunch of different races, the time they take is going to depend upon the time that they run that race in will depend upon the distance that they're running, which is a little weird. But at the same time, if they're running, um, the distance that they have traveled in one race will depend upon the time that they have spent running in that race. It's maybe I'm being a jerk here by using the exact same words for both of these, but it kind of does depend on how you frame it. So, scientifically speaking, I would generally say that the independent variable is your cause and your dependent variable is your effect. So look at your two variables and decide which one you think is the cause and which one you think is the effect. And then it'll go from there. All right, so anyway, If we rearrange this, we could see that if we leave y where it is and solve for y, right, we can subtract 2x from both sides, and we get y has to be greater than negative 2x. So again, the more negative x is, the larger in the positive direction y has to go in order to balance it out. Which also means that if x is a positive number, then y doesn't have to be that big. It could, in fact, be negative, if only, slightly. But y can be anything larger than negative 2 times whatever x value was picked. Ayo. Yes. So if x is 1, y is 1, you've got now 1 is greater than negative 2. So that's true. This is saying that there will always be at least one y value for any x value that we choose. Yeah. So this problem, the answer, if you're going for validity of this particular argument, right? The fact that you can choose any y. Nope. The fact that you can choose a y for any x value. And then they have this pattern. So again, y has to be more than double x in the opposite direction. Yeah, you just typed the same thing. If you typed it the other way, if it was there exists an x for all y. Oh, okay. For all x, any y can be chosen is going to be incorrect, yeah. Because you're not able to choose just any y. Yeah, because again, all you need to do is rearrange stuff a little bit, and then you've got the exact same. Um, I mean, it's the exact same function essentially. You're just saying solve for x now instead of y. So if there exists an x for any y that you want, then again, you just need to show the relationship that exists between the two. So solve for the variable that you're trying to choose. In this case, well, in any case, it's going to be the there exists variable. Why not? Oh, I see. Okay, I see. Yep. No, you're right on that one, because, um, hey, Superman. No, you're right. You're right. So, right, so if you turn it into words, it's a little easier to see. So there exists an x such that for all y values, this is going to be true. So, yeah, it's not going to work because we would have to have every single y value tested. And this is saying that, well, if we go the other way, right, solve for x, 2x is greater than negative y, x is greater than negative 1/2 y. So this is saying that we could actually choose y values such that this fails. This is saying that this should always work. This is saying, well, actually, this has bounds. Yep. Whereas in the upper one here, this said, for any x value you choose to pick, there will exist a y value. So you're looking at your x, and then you're saying, for this x value, I'm going to choose my y value. For this x value, I'm going to choose my y value. For this x value, I'm going to choose my y value. Whereas in this case, again, there exists an x such that for all y, 2x plus y is greater than 0. Yeah, this is a symbol that it looks like you all aren't using, but we use it almost all the time in, like, math proof level. It means such that. So it really kind of breaks up this argument into a little bit easier parts. So there is going to be some x for which all y's will satisfy this equation. So that's going to fail. Oh, I see. Hmm. Okay. So apparently people have just been using ST for such that. Hmm. Huh. Alright, so for whatever reason, my teachers just dropped the ball on that one and started using something completely different. Oh, yeah, yeah, yeah. There it is. Somebody has this. Hmm. Um, David Vandershell, PhD, math and physics at Rice University, said that when he was a student at Rice in the 60s, many teachers used the backward epsilon like I have here. In LaTeX, the slash in LaTeX code, the is an element of is slash in. And I think you're right. I mean, clearly Superbrain's right, but um, but somebody decided to get cute, and so the LaTeX for this one is slash ni. Clearly, the people who use who created LaTeX were having a good day. Um, very interesting sense of humor. So anyway, yeah, this guy who was a student at Rice no longer sees this to mean such that in any of the stuff he does. So ST is going to be the common abbreviation. Somebody else said also such that can just be the single vertical line. Somebody else says colon. So yeah, Cap and Cupper, an interesting LaTeX choice. Um, I typically don't use Cap and Cup in common parlance just because it's difficult enough for some of the students. But and not to mention in my actual class where we use it, it's sharp, so it's not union intersection. It's points. Oh, I see. Hmm. That may have also changed recently because I feel like I remember Cap and Cup were a thing in LaTeX. Anyway, wedge in V, yeah. I mean, they're both wedges. All right. Anybody have any other questions while we're here? Yep. Good night, Bertram. See you later. No! It's ridiculous. All right, anyway. Yeah, Super Brain, we got past the first problem. So this was defining, the book is also defining absolute value as like the next thing. And so I said, okay, well, also I'm going to define it slightly differently, just as the different distance between x and some other value c, specifically. So that this could be generalized to anything we want. So if we let c be 0, then this is going to give us the things from up above, and this allows us to have x is less than or equal to the absolute value of x in all cases, and also the absolute value of x times y is going to be equal to the absolute value of x times absolute value of y. I mean, it's fine, but I'm specifically generalizing it because it comes up specifically in my class. Maybe not exactly here in this particular book, but yeah. So like I said, I just framed it differently and made it, specifically, let's look at it as the difference between any two numbers, distance between any two numbers, and then anybody who wants to specify, I'm just using c equals 0. That's perfectly fine, like we're doing in the following case. So x is less than the absolute value of x, and the product of x, y, absolute valued, is equal to the absolute value of x product, absolute value y. Okay, so then 1.3, proposition 1.3 is going to be the triangle inequality. Absolute value of x plus y is going to be less than or equal to the absolute value of x plus the absolute value of y. So I'm going to prove Okay. Oh no! I almost forgot to do trivia today. And then I was at work and I was like, oh, wait a minute. I have 5 free minutes. I can look at the questions at least. Didn't answer them until I got home. So, taking cup. Got any specific questions you're interested in, or? Okay, so let's see. If I use these things, right, I can't really use a whole lot else. So I've got to start from here. And I think that I can get away with this. If I do, nah, all right, cool. X plus y is going to be less than or equal to the absolute value of x plus the absolute value of y. And also, oh. Okay. Absolute value of x plus y is going, no, other way. Okay, so x times y is going to be less than or equal to absolute value of x times y. Because in this case, we're just saying that x times y, the product, is going to replace x in this upper stuff here. So the product xy must be less than or equal to the absolute value of the product xy and the absolute value after. Then this is going to be equal to absolute value x times absolute value y. And I'm liking my chances in order to figure out some sort of like squares thing. I don't need that. That might be too complicated. Alternatively, we might be able to use section 1.1 up there. If a is less than b and they're positive, then the square root of a is less than the square root of b, and a squared is less than b squared. ab is in the middle. So here, so let's take this over here from 1.1. We've got so this was already proven. If 0 is less than a is less than b, then 0 is less than the square root of a is less than the square root of b. So 2xy less than or equal to 2 absolute value x, absolute value y. Okay, okay. So if we add this one and that one together, then we get x plus 2xy plus y. Nope. Close. So close. Because that's not x squared and y squared. All right. This is one of the problems with math proofs. Oftentimes little things like this can take a while. All right. Oh no, out of water. Well, harumph. All right. I get the same problem with puzzle games too. Just sit here, try to solve them, and people are like, ah. All right. I mean, like, it's a 2-line thing in my book here, so, like, can't be that hard, but... I thought I had a way in with the binomial expansion. So it's getting kind of close to that. All right, I'm gonna probably start fading out. So let's start. Let's find somebody to raid on. Otherwise, this is just gonna go poorly. Oops, that's not what I wanted. Stremenger. Alright, I think our usual raid target of Jason Charles Miller might be... Certainly he isn't awesome. Yeah, alright, let's do it. So we're going to head out and see Jason Charles Miller. Thanks everybody for coming, and I hope you have a good rest of your week. I will see you on... nice. See you on Friday for games, and next Wednesday for more math stuff. So this is Obi-Wan Pez for Ensign Plex Pachinko. Have a good night.